So who am I? I'm Cainã Max. I'm Brazilian, a data scientist, PhD. I'm currently working at Schlumberger, SLB. It's a company, a technological company that works mainly in the extraction of oil and gas. My hobbies, I enjoy spending time with my family, friends. I have a daughter, a dog, and a cat. I started going to the gym, love traveling, and love songs, art as a whole. So songs, music, TV shows, and of course I love programming. So I have contributed a while for the Stack Overflow. So my career basically can be split on inside the academy. 7 years doing since my bachelor in biology to the PhD in genetics. And after that, I started working to the industry as a data scientist. So I work in a financial company called Remessa Online. Then I worked on the AB NumBev Tech. That's the tech hub of the AB InBev and the largest brewery company in the world. So if you enjoy beer, probably have consumed some of our products. And now I'm working at Schlumberger. Okay. So, and I also work as a consultant and teacher to a school called DNC that teaches about data for foreign people. So feel free to reach out to me to the LinkedIn. And let's begin. So why did I choose this topic? Well, data leakage is a flaw in machine learning that leads to over-optimistic results. So I'm telling you that because my personal experience. So I have seen a lot of code from students. Have read a lot of blog and social media posts, and I have seen some issues also in some amateur courses about it. But it's not only me, it's not only my perception. So recently a paper was published on September this year that identified at least 494 papers across 17 different scientific fields with leakage issues. So with this workshop, I hope that you're going to learn what data leakage is. You want to know how to avoid data leakage in practice for your own code. And of course, you're going to know how to identify data leakage on someone else's code. Okay, so we're doing by using machine learning pipelines, using open source libraries like scikit-learn, imbalance-learn, filtering engine, and so on. The focus here is going to be on scikit-learn. Okay, and yeah, let's understand how machine learning pipeline works elsewhere, because all machine learning frameworks use a similar pipeline under the hood. So that's what I'd like to show to you to get familiarity with how pipelines work. Okay, so if you are highly familiar with machine learning pipelines, if you're confident that we're not promoting data leakage on your project, maybe it's not very worth it, this workshop, but that's an introduction. But yeah, let's see. So what's the requirements? It's good to have a basic machine learning knowledge, at least for this theoretical part. We're going to talk a little bit using slides, then we're going to practice a bit. And it's a place to have a familiarity with the scikit-learn. It's really good. For the practice, it's mandatory to have Python knowledge and pandas as well. So it's really good to have a basic machine learning knowledge and a basic familiarity with scikit-learn as well. Okay, so what's the agenda? I'm going to start reviewing some concepts of machine learning life cycle to be sure everyone is on the same page. I'm going to talk about data leakage, definition, how some common mistakes when you are talking about data leakage, and about pipelines using scikit-learn as an example, so that you can avoid some of the mistakes that you can commit about data leakage. And then finally, we're going to have some hands-on, okay? We can see the repository here. I need to update some things, but the majority of the code is already over there. I'm going to use Colab here just to highlighting some concepts. So let's begin. Well, just a reminder, the machine learning life cycle works like the CEO, someone has a demand that's going to give it to the project manager, and occasionally it's going to reach you, the data scientist. So the data scientist has the role of understanding what's the requirement, so that's the business understanding. Then you need to understand available data, if it's feasible or not, what data it's available for working on this issue, this problem. And then it has to prepare the data, to model the data, evaluate the model, and then finally deploy the model. And after that, it needs to monitor the deployed model, okay? But let's stick to these main sections. So the machine learning pipelines works a little bit in this, fits in the data preparation, data preprocessing, and modeling. And it's also essential for a proper evaluation. So let's start talking about the evaluation. So when you're working with machine learning, mainly supervised machine learning models, we need a test set. So we need to leave out some data so that you can compare the metrics of our trained model to see how well it's performing. So that's the fundamental of machine learning, right? So there are several techniques to do that. The simplest one is to just split the data across training data and a test set. Okay, but here's the deal. Not only the model should be trained on the training data, but also the preprocessing step should be done on the training data. And you must use the same preprocessing step applied to the training data to the test data as well. You must be sure of it. Okay. If you, for example, another way to evaluate our model is to leave a test set to provide metrics, and then in the training set we can either split apart for validation, or you can perform a cross validation. So here, each blue fold is a test set. And again, this test set should not be preprocessed separately. I mean, you need to use the same parameters from the model and from the preprocessing step using this training data over here. Okay, so it's very important. And why is that? The test data should know nothing about the training set. Okay, it should be loyal to the reality of an unseen data. That's why. So you want a good generalist model. You don't want a model that memorizes the training data. And to be sure of it, we need to keep a very good split between the training and the test set. So here we have another way to look at the machine learning life cycle, focusing on the data preparation modeling. For the data preparation, we start doing the data analysis, and then we are going to process the data, a process called filter engine. Okay, then we might select the data to build the pipeline. So here is where the machine learning pipeline comes. The feature engineering can involve several steps. Some of them are mandatory for machine learning models. For example, missing values. We cannot have missing values. Most of the models we work don't handle missing values natively. Okay, even though the ones that has handle missing values, it's not like they are doing something like we can do before sending to the model. Okay, categorical values. The models doesn't accept a string as well, so we need to transform it into numbers somehow to encode. Okay, some topics to be aware of is the cardinality. If you have a high number of labels, it's going to increase a lot the amount of columns in the data. So it's going to be computationally expensive and prone to overfitting. You can use rare labels to rare to label in frequent categories for avoiding this problem. The distribution, a better spread of values might benefit performance for some models, and outliers can be impacting some models as well. For example, linear models, distance-based models is going to be impacted by outliers. So here are some topics, some pre-processing techniques that you can apply. Okay, you can apply numeric feature scaling. Depending on the model is going to be important. For example, again, linear, generalized linear models, distance-based models, models that, some models that, for example, logistic regression that use a gradient descent to find the best parameters. So it might benefit from numeric feature scaling. The categorical feature encoding, it's important, like I said in previous slide. So we can apply on hard code, ordinal frequency and time encoding. We can also apply feature selection, for example, dimensionality reduction for reducing the amount of variables in our data, for example, PCA. We can use variable importance, like correlation, using some kind of correlation values or tree-based models. And you can also provide a regularization to decrease the weight from some variables. Feature transformations can be important as well. Feature interaction, and for example, product of two variables or some custom combinations. And sometimes you need to handle data imbalance. So there are some techniques to do it. And in all these examples here, we need to do it in the trained data so that use the learned parameters, pre-processing parameters in the trained data to apply in the test data and the future data as well. It's going to become very clear when we start the hands-on. Okay. So just a note, depending on the data type, for example, text data, time series, and image, distinct pre-processing techniques should be applied. Okay, we're not focusing on text, time series, and visual data images in this workshop. So, okay, we have the framework pipeline, but when does it break? It breaks when the training data includes information that allows the model to make predictions that it cannot make in the real-world scenario. So it usually leads to over-optimistic results, okay? So that's actually the definition of data leakage. An analogy would be, for example, it's like having the answers or some tips of the answer to an exam in advance. So it doesn't truly test your knowledge. It's the same for the models. Okay, if the model knows something, some tips, some clues about the test data, your metric of the test data is not reliable anymore. Okay, so that's why I said that the leak is a flaw in machine learning, and data leak can lead to multi-million-dollar mistake. It's a multi-million-dollar mistake that in many data science applications can reduce the increase the cost for the company. Okay, because let's suppose, for example, a churn problem. Your test data, a churn problem with a data leakage. So you're saying to the stakeholders that the metrics is fine, it's good, it's excellent actually, but when it comes to production, when are you going to know it's not good? It's going to take some weeks or months. So by that date, we have probably the company has taken some actions based on your model, and this action is not resulting in any benefit to the company because it's based on an unreliable model. Okay. So here we have some common reasons. Again, taking the paper I mentioned before. So the most common, in my opinion, is the lack of a clean separation of the training test set. So usually it might happen, for example, if there's no test set, it's the worst scenario. But even if you have some training test set, but you preprocess, you apply the same preprocess technique to the training test set. For example, the fit on training, the fit on test, feature selection done using both as well together. If you have duplicates in the data sets, can lead to data leakage because let's suppose that we split the data randomly, and they have 3 duplicated records, 3 information from the same customer. So it happens that you can learn the pattern of this customer, and then you're going to test again this customer, because this customer is duplicated, is also the test set. So we need to remove it. Another issue is, for example, model use feature that's not legitimate. So a good example is to use a feature that is not available at the time of the prediction. You have in your data because you have the labels, but in the field, the major goal is to apply a model on unseen data. I mean, on data without the labels, so that you can predict the labels. But in this case, you not have it. Or, for example, you can also have some feature that's derived from the target. So let's say again churn. If you have the variable churn, and I also have the variable, for example, the reason for the churn. You cannot use the reason for the churn, right? Because it's kind of the same information. Again, it's derived from the target directly. Finally, for example, the test set is not drawn from the distribution of scientific interest. So if you're dealing with time series, for example, you need to apply time series split on the data. So taking only the last values for the test, which you may not, for example, randomly split your data for time series. If there's some sampling bias as well. So for example, if you train using people from geography, in a test set is very different people. So a bias also going to impact the data. And one example of it is, for example, when we handle imbalanced data. So you cannot, for example, change the test set at all. So you cannot resample the test set. You just resample the train set for training, and then evaluate it in the test set. Okay. And even so, if you go a little bit back here in the K-fold, it's important to notice that ideally the test set should not be used to tune the model as well. Okay, because if you're tuning the model based on the test set, you're kind of optimizing it for the test set. Okay, usually you either do a cross validation or leave a piece of data for validation for tuning purpose. Okay. And okay, this is a figure 3 that I took from the paper I was talking about. They have identified leakage on several papers. They chose one study case, papers from about Civil War, and from these papers they took only the papers that has available data and available code, so that they could reproduce the code. And then they corrected the results. I mean, they corrected the data using the proper validation, the proper pre-processing techniques, and then compared the results. So this here is the first category is without correction, is with data leakage in this case. In the second, we have a corrected results by the authors. So you see that the values decrease, sometimes decrease a lot, for example, in this first paper here. Okay. And yeah, you see that it's very common to have a pre-processing on train and test set at once before splitting the train and test set. So it's very common even inside scientific papers, because AI is a field that is growing a lot recently, and of course everyone wants to apply it, everyone wants to use it, but this kind of mistakes can happen. Okay. It's not only for the internet, it's from scientific papers, so that's very interesting. So what would be the solution for working with for handling the data leakage, for not doing data leakage in our data? So one of the possible solutions is using transformers and pipelines from open source libraries like scikit-learn. And why is that? Transformers and pipeline are specialized classes for machine learning frameworks that play a crucial role in the data processing and model building process. Okay, they are specialized for frameworks, so they work they work build thinking on it. So in scikit-learn, we have a pipeline. The pipeline can have transformers, one or more transformers. The transformer is going to transform, to change, to modify your data, your features. So you can think on it like the preprocessing. Okay, transformers it equal the preprocessing steps. The estimator is the model. Okay, that's the nomenclature convention that scikit-learn took. And how does it work? The scikit-learn it has, like I said, transformers, the estimators, the pipelines for captioning, to all of these, and also the column transformers. It's a special class to apply some transformations to specific columns. Okay, we're going to test it on the practice as well. But it's not only scikit-learn, because scikit-learn is like the pioneer library for machine learning Python. So a lot of libraries were built using the same structure provided by scikit-learn. So, for example, ActGBoost, CatBoost, like GPM, Feature Engine, and so on. So the pattern is very similar. So that's why it's very important. If you know, if you understand the pipelines from scikit-learn, it's quite easy to understand pipeline from other libraries as well. So talking about the transformers, that's how it works. So the transformers can be any kind of preprocessing step. A single transformer is like a preprocessing step, or a conjunction, or several preprocessing steps. For example, this transformer here, in this example, we're going to use the simple inputter. It can be the simple inputter, so that's going to apply transformation to the data. But first, you need to learn from the data. So instantiate this transformer. When you apply the fit to the data, it's going to save the attributes, the model state, so that they can use the same attributes to the test data, to the feature data, and all. Okay, and the same here for the standard scalar. Okay, when you fit in the touch columns, we need two attributes to reproduce this equation. So we need the mean and the scale, that is standard deviation. So basically, what's the formula for the standard scalar is like the value minus the average of values divided by the standard deviation. Okay, imagine that we are using this a new instance. We want to predict on a new instance, but we only have one customer. So how would I apply standard deviation, take the mean of a single value? So that's why we save these attributes from the training set. Okay. Okay. So fit is going to learn the parameters. Transform is going to use the learned parameters to be applied to the new data. And fit transform is going to do both of these at once. So basically, the first learn parameters, then it uses the learn parameters to transform the data. Okay. For the estimator, it's kind of the same logic, but the difference that instead of using the dot transform, you're going to use the dot predict. Okay, but it's also going to have the model state. For example, a simple linear regression. What do you need for applying linear regression? You need the coefficients and the intercept. So it's going to save these variables, these attributes, so that can be used on new feature data. Okay. What if we need to apply specific techniques, specific preprocessing to different columns? There is a smart way of doing that. Okay, using the column transformers. So basically, let's take, for example, this input here. We have some numerical variables over here, and you have two categorical variables. So we want to, for the numerical variables, we want, for example, to scale the numerical variables, and for the categorical variables, we want to provide one routing code to these variables. So by using this class, you can specify what you want to do, in which columns you want to do. Then it's going to split these columns, apply the transformation we want to do, and then it's going to concatenate it automatically. Okay, it's going to be saved in a kind of a transformer class as well. Again, this here is going to be more clear in the practice. Okay. And finally, you have the pipelines to encapsulate, to group all of these together. Okay, so what does a pipeline do? The pipeline can, for example, have a transformer and estimator by the end of this pipeline. So that's if you build a pipeline, if a transformer in an estimator, you pass the data and the target, what it's going to do? It's going to save the state of the transformer. It's going to apply the transformation to this data to get the output. It's going to use this transformed data as input to the model. And again, it's going to save the model state, the attributes from the model. Okay, the fit is done just once. Once apply the fit, we can have, for example, the attributes necessary to reproduce the predict function. So we need the mean of the inputter. We need the in this example here for the numerical variables, we're going to apply simple inputter. I'm going to scale the data, so we need the mean and the standard deviation value. For the categorical data, we need the categories that's going to, for each, from each categorical column, and this index if you would like to drop some values. For example, if you have a binary column, categorical column, you can select keep just one column instead of keep both of them. And then we have for the random forest, we have the estimators. So we have all the trees used for making the classification using random forest. After that, we can just predict the data. And why is that so good? It's good because it's simple. It's very simple, and it's very practical for deploying in machine learning applications, because you don't need to save every single transformer separately, because you don't need to save the attributes from here, from here, from here. It's just a single object that has all required attributes for applying the prediction. Okay. In a final note about scikit-learn, it has two ways of processing the data. One of the ways, this green here, we have classes. Okay, so for example, one hot encoder is a class, and that's what we use for pipelines. But it also provides some functions. For example, the min-max scale. We have the min-max scale class and have the min-max scale function. What's the difference? And the function is going to output results. It's not going to save the attributes required for applying to filter data. So it may be worth it to use it when you're going to use it just only once, for example, for a particular purpose. But if you want to apply to build a predict pipeline, a predict model, you should use the classes instead, because the classes store all the attributes necessary for applying the prediction, applying the transformation. Okay, so it's indeed it's even a note from the website. When you go to this page in scikit-learn, we see a note, for example, do not use scale unless you know what you're doing. Why they say that? Because they don't want you to use these in a pipeline. I mean, to transform the data using these, and then taking this data to a model, a supervised model, because by the end, when you're going to use it, you need to apply it again. So it's best to use the standard scaler instead. Okay, here we can go to the hands-on example, but before going to the hands-on example, do you have any questions so far? Is it clear? Please let me know by the chat. Okay. Okay. So let me stop sharing the slides. And I'm going to the notebook. Just a second. Clean output. And share the screen again. And, oh, sorry. Do you see the screen? Okay, so let's begin. Okay, I'm going to run some code with you, but here it's pre-written, but I'm going to go step by step if required. Okay, so the first thing I'd like to do is to install scikit-learn. Actually, this version is already installed on Collab. Okay, but it's very important for reproducibility if you're using this locally to have at least a version greater than 1.2 for scikit-learn. For scikit engine, I think you can install any version, should work. Oh, sure. Is it better? Okay, I believe it is. So this here is just for the didactic purpose, not for showing the wrap text when I print it. And I know best practice would be to load all libraries in the beginning of the notebook, but I think it's going to generate confusion. So I just load some of the libraries, but I load, import the other libraries, the other functions as needed. So Pico just for saving our models and transformers. Pandas and NumPy, you should be familiar. And Seaborn for visualizing. I don't think you're going to use it, but okay. Here I'm going to use an important parameter. Starting from, I believe it's 1.0 for scikit-learn, we are able to provide this configuration here. So basically, when you use any transformer or estimator, you're going to output a pandas table instead of an NumPy array. I mean, at least if the input is a pandas table, the output is going to be a pandas table as well. Okay, so I'm going to use this configuration, this setting, and okay. And here I'm going to load the pipeline, okay? But I'll talk about it again soon. The important here for now is the logistic regression. Okay. So first step, I'm not going to use real data here, since I just want to show to you how it works. First, I'm going to create fake data so that you can clearly see it. So it has few observations. As you can see, the training data has 5 observations, the test data has 3, and just a feature data that we do not know the label just have 1 observation. Okay, so that's the structure of our fake data. So we have 2 numerical features, 2 categorical features, and the target. Okay, think on it for example, a tool, any kind of tool that is going to use it and can fail or not. So let's say if it's answering if the tool has failed in the next job, for example, the next execution, next usage. Okay, so the last temperature, the last pressure, if there is any maintenance due, or the age status as a categorical variable. So first thing is to specify the variables. Okay, so I usually split into numerical and categorical, and then I have a then all together and the target. Let me do something here. Just a second. Just a second. Changing something here. Okay. Okay. Let's proceed. So first I'm going to manually processing all the features without using scikit-learn transformers and without using scikit-learn pipelines. And why is that? Is because I'm doing it because I'd like you to know, to learn how to understand, to fully understand how a pipeline should look like. Okay, so you're not using scikit-learn yet, but we are using the best practice of splitting the train and test sets. Okay, actually it's already split for us. We have some it's already split, and everything that any preprocessing step should be done here, okay, in the train set, and then the learn parameter is going to be used for transforming the test and the feature data as well. So okay, just a note, I'm not recommending anyone to take a manual approach like this. It's just for the didactic purpose. Okay, we should have in this case missing values, numerical variables and categorical variables. So here, let me raise something here. I'm going to paste it in case better if you do this way. So here I'm going to split the features from training and the labels for training, the same for test, and the features for the new instance for the feature data, and I don't have any label for the feature data. I just want to predict it. And you're going to use a very simple model for that, logistic regression. So for analyzing the missing values, if you, for example, if you try to predict it, to use the model in the data as it is, so it's going to fail. Why is that? Because we have missing values. Okay, it doesn't accept missing values, so it should handle the missing values. And how would you do it? We can drop the rules. That's one way. We can input the values, and there are several techniques to input the values. Here, I'm going to use the simplest one. okay, just to fill the values with the mean of the training data. Okay, so for that we need to compute the training data mean. Okay, so mean. So that's the mean for temperature and for pressure. Let me see. Okay. So let's begin it here. And then by using these, you can fill the input, the missing values for the training, test, and validation data. So train, how would you fill it? You can fill in A using these here. It acts like a dictionary. So for the temperature column, it's going to input this value. For the pressure column, it's going to input this value and so on. So that's the logic of the transformers from scikit-learn. Okay, it's going to save the attribute learned in the training data and apply it on every data that we want. So let's do it all at once. Okay, so I'm filling up the missing values from the training, from the test, and from the new data. Okay, but I'm not computing the average again from test and yeah. So that's how it should be done. So now, if you repeat this here, input it, right? Okay, so it works. No error. So it means that it's inputted. Then you can use this model to predict the new instances. So that's the comment. Without missing values, run is okay. And let's predict it. So no error at all. So here I have the results. So, but if for example, we try to run a predict without with a data with missing value, then we would get an error. Okay, missing value. So let's do it. So that's basically how we should view missing values if not using scikit-learn approach. And we need to save this these values somewhere. Okay, so you need to use these values to fill to input the values for test data and for every new batch of data that we receive. Okay, so let's do the sample data scaling over here. So the formula for data scaling, like I said, for the z-score is like getting that for each value you subtract the mean of the column of the feature and then divide by the standard deviation of the feature. So here we get a standard deviation just like we took the mean. Okay, that's the standard deviation. So we can apply the formula using the learned mean, the training, and using the standard deviation from the training. So here it's inputted. I am going to take inputted data sets, and then I'm going to use the means and divide by the standard deviations. Okay, from every column. And here, if you show, for example, a value that's here, it's there is no missing value, and it's also scaled. Okay. Now let's train the model. So I'm going to train the model using the inputted and scaled data. Let's see. Okay, no error. It's running okay, and our features were properly scaled. Okay, using the logic, the correct logic. So, but what now? If you want to use this model for new data, what do we need? We need to take the data, we need to input the data, we need to scale the features of the inputted values. Okay, so how do you do it? Let's here. So basically, we need to save all of these features. So for example, here we create a dictionary with all the values. So for the inputter, we need the average because it's taking only the average to input the missing values for every column. Okay. Here for the scalar, we need the average and the standard deviation. So I'm saving the average. I'm saving the standard deviations. Train one, and that's it. So here I don't need it. It's just for showing. Here I have the model that was trained on this data before. And then we need to save this somewhere because we need to load it and use it. So, for example, we can save it like this. So I'm taking the numeric processor parameters and save in the training processor. And I'm taking the numeric model here and saving the model. So if you see here, we don't have any data. If I run this, I'm going to have the peak values here. Okay, so once you load it, we need to load and to apply the modification to the data, just like we had done before. Okay, a lot of work. So let's proceed. Okay, let me go some piece by piece on this. So you can understand it. So again, so what we need so far, we need to compute this and store the means. We need to compute and store the standard deviations for scaling. We need to store the computed preprocessing parameters and in these pico files. We need to create, after that, we need to create a table with the inputted values. We need to create another table using these inputted values to scale the values. And then we need to apply we need to manually apply the processing to this table with the training parameters. Okay, but wouldn't it be better if you have a class for computing and storing the preprocessing parameters that's able to transform the data using the learn parameters? It'd be much better, right? And that's what scikit-learn do for us. Okay, but again, we're not using scikit-learn yet. Let's try to create a simple class to simulate what scikit-learn does, but a very, very simple class, okay? A very limited class. So let's say, for example, my simple inputter. And what does it need? It needs a function for learn the parameters. So it needs to learn the parameters. So from the data is x, okay? X should work, but I'm also placing y equal to none because it's a pattern from scikit-learn. Okay, if you want to use this class in the scikit-learn pipeline, you can do it. Okay, as far as we have the fit and the transform methods, and we have the y value here, even if not using it. In this case, we're not using it at all. So let's say, for example, feature names in is the feature names you see so far. Okay. So once you fit, this class is going to have the names used in the original received, the names of the column names basically. So and this last underscore is has a meaning in scikit-learn. Okay, it only happens when you have a fit on it. So basically, before a fit, you don't have parameters like this one, but after the model trains someone, the attributes learned has this pattern, a last underscore. So let's keep this pattern here as well, and we need the mean. Okay, the mean. Let's return the function itself. let's say here, my inputter equal to this, and okay, here you are. If you try, for example, to access this, don't have, it's going to throw an error. Okay, but if you fit the fit it with our data, let's fit it with the train data. Oops. Then we have the feature names, and should also have a mean for every feature. Okay, but we also need a transform, right? Here we are learning the parameters, so let's transform the data. So self x y equal to none, and return field in A. Okay, so I'm using the mean, you see, from the train feature. So it's good. And just for compatibility with scikit-learn, let's provide a fit transform as well. Okay. So the fit transform, what's it going to do? It's going to fit the data, okay, and it's going to transform the data. Let's see how it works. So here, fit, let's transform it. Okay, you are. It's now inputted. Okay, so before it was a missing value, and it's inputting with the average computed. Okay, temperature is going to input with this value. Okay, here, and pressure is going to input with this value over here. So let's try a fit transform here. Okay, it's working as well. So that's one of the ways you could do. Of course, I do not recommend anyone to do that because there are best worked classes from scikit-learn for doing that, but just for showing to you how it works under the hood, a very simplistic approach. So let me paste it. Okay. So here, okay. If I don't have the if I don't have fitted the data, I don't have the parameter. After I fit the data, I should be able to see the learn parameters. Okay, so let's transform all the data, and it works okay. Okay, no error was launched. And let's see before and after the implementation for the test set. Okay, use our classes. You fit our class to the train data, and you are using the parameters learned for the test data. So here's how it looks like. Okay. So let's do a similar approach for the standard scalar as well. The standard scalar, you need the average and you need the standard deviation. So how should you do it? I think it's very similar. Okay. So what do you need? We need the mean. Once we fit in the mean, we need the standard deviation. And okay, that's it. After that, we're going to use to return the transform data. So the value minus the mean divided by the standard deviation. And here's the z-score. Finally, the fit transform just to show here, to encapsulate both of them together. So here, let's say take the inputter. We need to train the inputter, and here these scalars should be done in the data with no missing data. Okay, so we're taking the actually transformed. Here, my inputter and my scalar. So we have the tested train, trans, inputted. So train inputted, it's this train fit transform. Okay, it's here, and then you can provide a scaled version. So you take my scalar, fit transform using the inputted table, and then it should be inputted and scaled the right way. Okay. So, and you can use it for new variables as well. Okay. So let's, for example, do something here. Read this. Okay, here I'm learning the parameters, the attributes, and then I can apply it to the test data as well. So how should I apply the test data? First, you need to apply the inputter. Okay, transform the test data, and using this, I apply the scalar. Okay, transform. Okay, so first imputation, then scaling, and here you are. Okay, so I can do it for the test and train data as well. Right here. I didn't talk about pipelines yet. I'm going to talk it pretty soon. But like I said, if you want to use these classes in a pipeline, we can do it. So, for example, I'm going to show to you how to create a simple pipeline here. Pipeline. I'm going to press all the transformers, okay, ordered. So it's my inputter, it's my scalar, and you can apply the logistic regression. But for now, let's just keep just this. Transform pipeline. Then we can use fit to our data. Okay, and here's the pipeline. We use the simple inputter and the standard scalar to all features. Then you can use this to predict new data. Let's predict, not sorry, to transform the data. So transform. So not model is transform pipeline and transform. Okay, let me show it to you. So here I'm going to print the. Sorry, I think it's best to just do this here. Fit transform. Okay, you can use it in the train data, the test data, and the feature data as well. But if you want to also include the model to transform the data and take this transformed data to predict the class, the target class, we can do it. So let's just variation. Okay. Okay. The only difference that we are also going to need the trend value, right? We need the labels, features, labels. Okay. So what we do? You apply our simple inputter, then our standard scalar, then the logistic regression. It's going to store all the attributes from these objects so that can be used for transforming new data. So in this case, not transform, let me change the name. It's a model pipeline, it's a whole pipeline. And then I can predict new values. Okay, the predict is going to apply the transformation and the predict function. Okay, if I can do it for all the data, so okay, I can apply it to the train, to the test, and to the new. And here we are. Okay. Again, we can save the preprocessor. Okay, we're going to save it numeric inputter and a numeric scalar. I'm saving it separately. Okay, so here we have inputter and scalar. So let's talk about the categorical features. Okay, here I'm selecting the categorical features, okay. And let me show it to you. We have these two columns over here. Okay. Let me again erase some things over here. Okay. So my first suggestion is not using pandas get dummies because it's going to apply different preprocessing to every dataset. It relies on the dataset. It doesn't have this intuition of applying to a train set and save the parameters so that they can be applied to new datasets. Okay, so for example, if I apply pandas data get dummies to every distinct set that we have, we get this. Okay, for the train data, that's our result. For the test data, you see here we have an extra column. So there's an extra column here. And we have, for the new data, we have only one observation. This observation is one for this and one for this. It has no do maintains, and the age status is new. So what happens if we fit this here? So what is the mod? Let me just see model. Okay. So here trained using this extra transformed, just to remind you, transformed looks like this. So that's the transformed data set. And let's fit the model. It worked here. And let's try to predict something else. So let's predict the trained data, the same one you trained, right? So it's okay, no error. Let's try to predict the test data. Okay, it fails because it has an extra column. So our model is already broke. I mean, the table, the structure is not working here. And if you try to predict the new, it's even worse. So I have two features that's missing. Okay, categories, two categories seen in the trainer that's not seen in this new data. So it's going to broke the model. So that's why I don't recommend using predict dummies like this, because it's equivalent to use fit in the scroll transform to the train test and new data as well. So let me raise it here to go with you. Okay. So let's create a minimal class, okay, for computing the dummies, okay, properly. Okay, transformation applied only the trained data. That should be applied also in test and common data. Okay, so let's call our class my one hard encode. Okay, Oops, didn't finish. And we need the fit. So I'm going to self x and y equal to none for maintaining compatibility with scikit-learn. And then let's call the categories here. And the categories would be the feature here. So basically for something, I'm going to take the feature in the columns, available columns. So basically want a set. So feature is equal to a set of she's feature. Okay, why is not feature? She's okay, what's wrong here? Okay, it's missing a comma. Okay. So here, if you do this, let me show it to you. And let's see the categories. It doesn't exist, it's going to fail, right? But if you fit the she's train, what? Let's see what happened here. She's hits and she's counts. Non-times is not as not attributes. Non-time. Okay, I need to return the object itself. Okay, so for do maintenance, I have these two categories. For edge status, I have these two categories, and so on. So basically, this is the information from the training. And this is what we're going to provide by the output. We need an output where the table contains a column for this, a column for this, a column for this, a column for this. You don't want extra columns. You don't want fewer columns. Okay, I mean, only if in only the case you want to drop one of the binary variables, okay, that's acceptable. So, but in this case, you still need to capture store other possible categories, and you need to create another attribute to show what category should drop. Okay, but in this case, we're going to keep all these categories over here. So, okay. So here I don't want only this, I want the table itself. So output columns, what is going to be the output columns? Then I'm going to use PD guardians, but only the train data, okay? Train, and I want the columns here, columns to list, okay? So here, if I see the output columns, I see all the columns I should have, not only for the training, but for the test, the future data as well. So that's the columns we have in the final table. So let's use this instance here to get. So transform some trees. Okay, so let's say trees in the line y x1 transformed equal to here you can get dummies, but there's a trick here. You can get dummies, but force to use the same columns over here. So pandas has a function for it. It's to index. So I want only these columns. If the columns are not present, it's going to return 0. I mean, sorry, it's going to return missing value. But the column is going to be present. That's important. That's what we want. And in this case, in the case the column is not present, we can fill like 0 because it's not present. That's the meaning. And finally, you can convert it to integer. So let's test it. So, okay. I just feed the data. Let's transform. Transform Okay, I haven't returned the case here. Okay, so for the training, if I fit with the training and transform the training, I have these columns. Oops, something's wrong. Reindex. Okay, I need to reindex the axis equals to 1. Okay, I just want to keep the columns, not the rows. Okay, so here it is. So now I have the output. If I apply the transform for the test data, it's going to work as well. Okay, I'm forcing to have this structure in my code. And here, that we have only two categories, is going to show the 4 variables as well. Okay, so okay. Finally, let's provide a feed transform. So, okay. Okay. So here I'm going to use the feed transform on the training, and for the test, I'm going to transform the test in the new data. Finally, let's show. Okay, same structure, right? Now I can use it in our model. Like, okay, let's test it. I'm fitting it again. I'm fitting the model, the logistic regression model, and then I am predicting. Okay, it works as well. So nice. But the next step is to save the categorical processor. Okay, so I'm going to save the categorical encoder, the categorical model over here, and it's here. Okay. If, for example, if I need to load this here, let me load it. We can okay, load the encoder, it's in Pico. Okay, just load the encoder, and also loading the model. So what is this? Is our class, and here is the scikit-learn model logistic regression. Okay, so now I can apply this to our data. So I need to process for data, right? It's already fit. I don't need to fit it again. Okay, I fit, I saved, I load, and then I'm using it because the attributes are already learned. So transform model file. Oh, sorry. Let's test example. Okay. So yeah, here before diving into the machine learning pipelines, we are almost there. I would like to make sure that it's fully understandable, this part of how it works. I think we can take some 5 to 7 minutes before going to this. Let me, okay. So far, how is the understanding? Oh, I just saw a question in the Q&A. How do you suggest to do pre-processing best practice in a manual way? Like if you know the dataset has missing values and how do you suggest best practice for that? The best practice is doing exactly what I'm doing here. You need to create the instances, the classes, to fit it, save it. Once we save it, we're going to load it and use the learned parameters, just like a scikit-learn will do. Okay, and that's the whole purpose of this workshop and this exercise here. We spend a lot of time doing a manual approach that no one is going to use it, but that's my point, because if we're doing the manual approach the right way, it's going to take a while, because it's not easy. It's not. We need we need to do all these steps that I just showed to you. Okay, I cannot just take the pre-process the whole data and then split the train test data. So and that's the magic of the scikit-learn transformers and pipelines I'm about to show, because it's easy. Okay, it saves. It's all. It's abstract. I mean, it's everything there already. Okay, 5 minutes. I'll be back. Okay, so okay, let's keep going. We're almost getting to the second transformers and pipelines. It's easy once we understand this. All of these have been talking so far. The scikit-learn does it like very quickly and efficiently for us. So what if I want to work with the whole feature? So far, I have processed separately the numeric features and the categorical features. What if I want to have a single class, a single function to process it all at once, while being able to specify the transformers? So that's what I'm going to do right now. Okay. So here I'm selecting all the features, not only the numerical ones. And we're going to load all the preprocessors and transformers, the manual transformers that we have made. Okay. Okay. So I have the numeric inputter, I have the numeric scalar, and the categorical encoder. Inputter, scalar, encoder. So how can we apply these like to simulate a scikit-learn pipeline? So basically, you can use the reduce function that recursively applies a functions to our data. So basically, let's say we have one table as input data and three functions. So it applies the first function, get the output of this first function. This output is used in the second function. Then this output is going to be applied to the third function. Okay, so here I have created a function called preprocess data that receives the X data, the numeric feature list, the categorical feature list, and the numeric and categorical processors. Okay, it's going to return the bonus data frame as well. So it receives the bonus data frame is going to return upon the bonus data frame. So first we apply the numerical functions. So we specify here the function. So basically, what I'm doing here, take this data that I'm receiving, and in this case, I'm taking only the numerical data. Take the numerical data and apply the sequence of preprocessors. So the sequence is this here, okay, numeric preprocessors. And I do the same for the categorical data. I'm going to have two tables, and again, I can concatenate them together. So let's see how it works. Here, preprocess data, I'm preprocessing the train. I have the list of numerical features, the list of categorical features is going to be the same over train test and feature data. And the transformers is also going to be the same. Okay, we have built it manually over here. And then I'm going to show this. Okay, she's transformed, test transformed, and new transformed. And here you have the inputted numerical variables scaled, inputted and scaled, and with the demo variables. Okay, it's kind of simulated pipeline, but of course very very simple. Okay, very limited compared to the scikit-learn pipeline. But that's what would take us without scikit-learn. But Now we have the scikit-learn. I mean, we have not only scikit-learn, we have feature engine, we have others, other libraries as well. Okay, and once you understand how transformers and estimators work together, you're going to understand how PyCarrot, how Amazon SageMaker, how DataQ, how other platforms work as well, because they use a pipeline like this. Okay, so without further ado, let's go straight to it. So uh, here I'm loading the simple inputter, standard scale, and one hot encoder. Okay. Indeed, I create this function here just to show the attributes from the scikit-learn classes. So it should end with underscore, like I discussed in the slides. Okay. Okay. So let's instantiate the inputter. So the scikit-learn inputter, you can see here it has some options for working. So it has, for example, strategy. I'm not restricted to the mean. I can fill up with the median. I can fill up with any other value, pre-computed value, and that's it. Okay, so I can specify the value here. I can also ask to add an indicator of missing values. So it's more complex than ours. Okay, and it works very good. So here is the inputter from scikit-learn. Let's see the parameters, the learned parameters. None. That's expected because we didn't apply the fit yet. So here I'm going to apply the fit and ask to show the parameters again. And now I have the parameters. So it has the feature names from the input table. It has the indicators in case this here is true. I have the any amount of features and I have the statistics. The statistics is the mean. In this case, is the mean. They not say mean underscore because it can also be other strategies here. So I see the same values that we have seen before in the manual approach. Okay, the average for temperature and the average for the other one for the pressure. Okay, so what if we place indicator equal to true? Let's try to see it and apply it to the numerical features. Okay, I have the same learned attribute here, and let's transform the train and test data. So if I add a missing indicator, it's going to fill to input the values, and it's also going to add a new column for every inputted column, telling if the value, if the observation was inputted or not. Okay, it can help some models this kind of information, so that's useful, and it's the same for the test. Okay, the trick here again, it learns for the train and use the attributes of the test and so on. For the send scale, it's kind of similar. Okay, so we instantiate the send scalar, we fit it. We have the list of attributes here. The list of attributes is different because it's a different transformer. So what do we need? We need the average and the standard deviation. So here is the average, and here is the standard deviation. Okay, equals scale. And you can also see here the transform data. Okay, I haven't applied in the missing in the inputted table. If I inputted missing, if it's inputted, then okay, here are. So, like I said, another way of applying the scalar function is using a function from scikit-learn, but it's not suitable for pipelines. Okay, you can use like this, returns an NumPy array. There's a trick to keep returning the pandas. Just apply the function like this. And here you have the function. So for the encoder, we have distinct kind of encoders. Let's show how the one-hot encoder works. It has several parameters compared to ours. For example, it has a very important parameters that is to how it should handle unseen features. Okay, if it faces a new feature, a new category, I mean, in a categorical variable, how should it take it? It can ignore it, so it's going to place 0 for all the observations from these, for all the categories in these observations. There is a parameter called drop. I usually use it with the value if binary. So if binary, you just want one column instead of two. I'm placing here sparse output equal to false because we are using the pandas setting here to return a pandas data frame, and that's it. Okay, let me place it on here to show to you. Okay, I just instantiated fit in the training data with the categorical variables, and I transform it. So yeah, that's here we have the values. We can trick a little bit from it. If you have a categorical variable with too many columns, we can set, for example, a minimum frequency over here. So let's say, for example, the minimum frequency should be half, 50%. Okay, so let's test it and see what happens. So here we see that the maintenance, yes, you have here, but the other column is like the maintenance infrequent because it has the node in this case has less than 50% of proportion in the training data. Okay, and of course this proportion saved is only considered the training data, so it can be applied in the future data as well. So, and here are the learned attributes from this class. So we have the categories, any index to drop, in the case we want to drop a feature if it's binary, for example. The infrequent categories, it saves all that is necessary for applying the transformation in new data. Okay. Another transformer is the ordinal encoder. So it basically it replaces the textual values by numbers, random numbers, ordered random numbers, but this ordered, I mean, it's random. Okay. It doesn't mean necessarily that 3 is greater than 1. 3 is a category, 1 is another category, but there is no meaning on the sense of magnitude. Okay. So we fit in the train data, the categorical variables, and transform that data. And here have the values. Okay. So what's the learned attribute from the encoder? Again, the categories and the feature name is in. Okay. So you see here the categories is here for no, yes. It's ordinal. So in this case, 0 is going to be 0. So sorry, no is going to be 0 and yes is going to be 1. The array is like new is going to be 0 and old is going to be 1. Okay. You see there's no meaning in the number itself. It's like random. So it's important to not apply it for if you're using any generalized machine learning model or distance-based model, is going to mess up with the patterns in the data. But if you're using tree-based model, for example, it's a good way to avoid creating too many columns to your model. Here is a label encoder, but the label encoder is suited only for the target variable, okay, not for the feature variables, as it is described in the documentation of scikit-learn. So you can, for example, apply train data and test data. So I have the original data over here. So, okay, true going to be 1, false going to be 0, and so on. Okay, so it learns this mapper and shows the classes. Okay, so what if you want to apply some transformers to specific columns all at once in an efficient way? So scikit-learn in other libraries provides something called column transformer that you can specify which transformation way to do in which columns. So basically you instantiate your transformers, okay? And you need to pass in this following structure. So inside the column transformer, it accepts a list of tuples. And each tuple has 3 values, okay, if you're using like this here. The first value is the numeric, the first value is the name of the step of this transformer, okay? So just calling here numeric. I'm going to apply this transformation here, the numeric processor, on these features. Okay, then I'm going to pass in other tuple to specify the name, the transformers, and the performance. So if I feed the train, I didn't. If I feed using the train, here's what it looks like. So for this is the name I gave to this step. So we have here the temperature, the pressure of the categorical have these, and I'm going to apply this transformation with these parameters. Okay. Once it's fit, I can transform the data easily. And it's going to provide to me the concatenated table. And it's going to apply the transformation to numeric, like I said, in the categorical, and then we can have the difference is that the name of the columns are changed. I mean, they use by default they use the name we provided in the column transformer for this set of transformers over here, right before in front of the column name. Oh, it's appeared. Okay, right over here. So what is the learned attribute from the preprocessor? So just remember this preprocessor is the column transformer that I have provided here. It's taking a while, not sure why. Okay, we have some attributes. The most important one is this here, the name transformer, because here you have a list, a set of transformers, and here that's how you can access the transformers. Okay, once it's fit, the parameters were already learned, and you can access these transformers separately. So that's very good if you want to debug, for example, something and so on. So that's it. So you can, for example, to take this simple inputter, they're called numeric, and I can apply it to the numerical variables. In this case, I don't want the prediction, I just want the transformation over here. There is another way of using the column transformer that called with this function here. It's essentially the same, but the only difference that it's not a list of tuples. You can pass the tuples directly, separating them by comma, and it doesn't require a name. Okay, you just pass what you want to do and in which columns you want to do it, and it's going to work as well. But it's going to provide for you the names automatically. We didn't choose the names here. Okay, it's taken a while, but it's working. Okay. So let's go to the pipeline example. So far we have seen the column transformers, and then if you want to use a pipeline, you can just use it inside a pipeline specifying like this. So let's see from the beginning. So here you have the product transformers, just like we have done before. Here you have the column transformer, just like you have done before, specifying the transformers and the features. And then the pipelines has this structure list of tuples, where the each tuple is a step name, a transform estimator. So you pass the step name, and then you pass the transformer or the estimator. In this case, first the transformer, then the estimator. Then we have this. Okay. After transforming, we have the pipeline from the model here. Another way to do it is using the make pipeline. Okay, the difference, again, you're not specifying the name, you're just specifying the steps directly without a list, and then you have it. If you predict it, it's going to work, and you can, just like the column transformer, we can access the steps of each step of the pipeline. Okay. I'm not sure why it's taking so long. Okay. Waiting for the steps. Okay, here the steps. Okay, so I have the column transformer, the name of the step, and the step is this one. Here is the name, and here is this one, and so on. Likewise, you can access a specific step with this way. You can also access it directly from the pipeline like this, and you can use it like usual. It's already fit. Okay. For example, for accessing the inputter, I should access the numerical transformer. Inside the numerical transformer, I can access the simple inputter, okay? And I can use it for imputation if I want. So a second example, let's say for the numerical features, I want not only the imputation, but I want the imputation and scaling. So I just apply a simple inputter here. I make a pipeline here with these two steps. Okay, here I use the categorical. But inside the column transformer, here's the deal, here's the catch. I can use a pipeline inside the column transformer. So with a step named numeric, I'm using this processor, which is a pipeline, to the numerical features. Okay, and here I'm using a pipeline to the with this preprocessor and the model. So basically, again, numerical is a pipeline. I use the numeric pipeline inside the column transformer over here. And finally, I can use a major pipeline where I use the column transformer, which has a pipeline already. So if I use it, that's how it looked like. So for numerical, now I have two steps. That's a mini pipeline over here, and I can transform the data to send it to the model. Okay, so and that's it. I can access the steps like these named steps. I'm going to use the preprocessor. Inside the preprocessor, I can access other features if wanted. So, for example, I have the model here. I call model. So I can access the model and get the parameters or change the parameters of the models as well over here. Okay. This I don't want this here. Okay, so let's see intermediate pipeline. I think our time is going to this. reaching. So intermediate pipeline, we can, for example, I just make exactly like before. I'm adding one extra step here. That is the PCA one. So I instantiate the PCA, and I can use the PCA as a posterior step to the preprocessor. Okay. Let's wait a bit. And time to run this. Okay. Oh my god, not sure why it's taking so long. Okay, now we have it. So I added a next step. It should be appear here right after the processing, and then I'm using the model to make the predictions. Okay, here it is. So here I have the PCA and the logistic regression. So it's intermediate, but that's usually what I made. My routine, I make pipelines like this one. Is more than enough for a routine on the machine learning. Okay, uh, but if you need to build a complex pipeline, I'm leaving here the code for you. It's on my GitHub. So let's say it doesn't make any sense to build a complex pipeline like this for these fake data, but just to highlight the possibilities, right? Let's say for the numerical features, you want to pre-process the numerical, the temperature input by the mean instant scalar. We want to pre-process the pressure with a median, imputation, min max scalar, and apply the PCA for these outputs. For the categorical variables, we want to input the most frequent category in case it's missing, and then apply one hot encoder. And in another step, I want to clusterize this output from the numerical and categorical variables, and I like to provide a new column to the table, giving the labels in a way that I can use the trained centroids for k-means to predict test data as well without data leakage. And finally, I want to apply a feature selection, automatic feature selection from scikit-learn to finally train my model. Okay, and I want to encapsulate it all together so we can do it. We can save just a single object and load this object for applying what I want. Okay, so by default, k-means has a predict method. So and a transform, but the original transformation for k-means it's returning the centroids. That's not what we want. That's not what we want in this example. In this example, we want to predict to learn the centroids and use the centroid for creating a new column. So I have made a small modification for this, okay, using fit and transform. And here I can show how it works, okay? So I instantiate it, I fit, and I'm transforming new data, okay? I fit on train and transform on test, and here I have a new column with the clusters, okay? Again, it doesn't make sense for this fake data, just for highlighting the possibilities, capabilities. So let's go step by step in this final example here. For temperature, I want two things: imputation of the mean and standard scalar. For pressure, imputation with the median and min max scalar. Then I would like to use these features. Then I'm going to apply. I'm going to apply this transformation to each of these columns. And finally, I'm getting this output here to apply a PCA. Okay, that ends our numerical preprocessing. For the categorical one, I like to input with the most frequent category and to apply one hot encoder. And then here I have the preprocessor for the numeric and categorical data. So I start with this preprocessing. Then I apply our custom function to create a new column to this data without data leakage. And then I'm going to select, choose a feature selection, selecting the two best features in this example, and finally applying the machine learning. So that's how it looked like. So for the numerical, I have what I want, applying PCA at the end. I take the processed numeric and categorical variables to pass to the k-means. A new column is going to be added. Then I'm going to select just a subset of columns, and then applying the machine learning. And then you can see how it works. Yeah. So we have further additional materials that it's available to you on GitHub. I will change it a little bit for clarity, placing more comments, but I think it's important to know that whatever library framework you use is doing that behind under the hood. For example, PyCurrent is a very automated approach capable of loading and providing several transformations of the data automatically. For example, here we load the data, we instantiate the setup, and with one single command, we have a lot of models for the particular variables, features, and target. Okay, it is ordered by the metrics that we want, and that's it. They're also capable of providing the by tuning, automatic tuning, ensemble, evaluating, and so on. But by the end, after we finalize the model, that's what you have. You see, you're probably familiar with it already, I hope. So that's what you have behind under the hood from these alt-amiel frameworks. All of them use pipelines in a way that he learned the parameters, and is able to use the learned parameters to new data. Okay, it's just a huge abstraction of the pipelines. So far, any questions? I'm sorry about the time. I would like to explain more some more things. Again, the notebook is over here. For the machine learning pipeline, I just put for the for the PySpark ML. I'm not going to show it to you, but only from the import you can see it's similar, right? From PySpark ML, you can import the pipeline. You can import the stand scaler, the on-hot encoder, and you can use all this preprocessing and estimators to the pipeline. But this case is a pipeline built for PySpark. Okay, but the logic is the same. You can use the same DEX we have seen so far.